Hey everybody, I wanted to spend a little bit of time talking about metals, going over coordination compounds, maybe a little bit of how to determine the charge on transition metals, maybe a little bit of structure and that sort of thing. So I guess we should get started talking about isomerism, and isomerism has everything to do with structure. Okay, so if we're talking about kind of maybe similarities in how we may have learned maybe ionic compounds or even covalent compounds, molecular compounds, we may have learned like how to determine charges, and maybe we've learned formal charge, and then we talked about structures, Lewis dot structures, and then maybe we discussed names. Well, here's the something that has to do with structures of these guys. Okay, and so there's something called isomerism that runs throughout chemistry. Isomerism is when you have an element that, or when you have a compound that has the same formula, has all the same elements in it, but it's connected differently throughout the compound. And so when we're dealing with metal compounds, there are two classifications of isomerism that we deal with, and one of them is called geometric isomerism, and the second one is called structural isomerism. Okay, so geometric isomerism has to do with the kind of how the elements are bonded to the metal. Okay, so when we went through the naming and when we went through that sort of thing, you can have the metal attached to a whole bunch of things here. Let's make it like this, just easy. Okay, Cl and then Cl. And then all of this will have a charge, whatever that is, and then it'll have a counterion. So maybe this had a charge of 1+, so we need 1 bromide. And so a coordination isomer is when this guy switches spots with this guy, and this then becomes, well, let me erase it and show you here. Okay. So now this is a Br here, and this is a Cl. And so the relationship between those two things are isomers, okay, and that means that those compounds have two, in general, totally different physical and chemical properties. The way that it's bonded is different, making them have different properties. Now, linkage isomers are kind of interesting because there's some ligands that are kind of long, chainy looking things. Okay? And when I say chainy looking things, I don't mean like Dick Cheney, the vice president of the United States back in the day. I just mean long, chainy looking ligands. And so one of the common examples is thiocyanado, which is CNS. Okay, so it's cyanide. Let me make sure that I put this correctly here. Okay, thiocyanado. Okay, and if we're going to draw this correctly, I think we will have something like this as its structure. Okay, now I'm doing this kind of off the top of my head, but I'm not sure it's necessarily going to matter. So what's going to happen is that, notice we have lone pairs of electrons here, and we have lone pairs of electrons here. So this ligand can attach to the metal here or it can attach to the metal here. That gives it different connectivity based on how it links, hence the linkage isomers, to the metal. Okay, so if you have the metal here, and now we have it as SCN, and I'm leaving off stuff, that's one isomer, or you have the metal in the middle, and there's going to be other stuff attached, but then NCS, this gives you a different isomer, and those are called linkage isomers. Okay, provided that all of these things are the same. Now, there's other neat kind of isomer called structural isomerism, and the only one that I want to really talk about is going to be cis and trans structural isomerism. And so you may recognize these prefixes where cis means same side and trans means across. Well, this compound, this is called cisplatin. Okay, now we have platinum in the middle. Okay, and we can have NH3 Cl NH3 Cl, and notice that these two ligands, the ligands are across from each other. That is the trans isomer. Okay, that's not the one that is famous by any stretch of the imagination. It's actually called transplatin. So the one that is famous is the cisplatin, where the chlorines are close to each other, kind of on the same side as the ammonias, and so that is cisplatin. Now if we draw a line, this is where it gets same side. Notice the chlorines are on the same side and the ammonias are on the same side. Here they're across from each other. So that's cis and trans isomerism. I get it. It can be a little confusing, so let's take a look at some of these things. Okay. So here we have three different complex ions or coordination compounds. Okay, well here's a complex ion. There's no counter ion, complex ion, and this is a complex ion. So let's see if there's any if there could be geometric isomers. So geometric isomers exist when you have an ion that can switch spots with the ion that is the counter ion. So if we look here, this is only going to be cobalt, CO, and then it's going to have a nitrogen, this thing, and then this thing, and then this thing. Okay, and then SCN, SCN, and then SCN. Okay, so this guy doesn't have any ions to counteract where they can switch spots. So this cannot be a geometric isomer. Okay, can this be a linkage isomer? Well, lo and behold, the example that I had was with thiocyanate. So sure, complex ion number 1 could be a linkage isomer. Now, could it also be a coordination isomer? Can it have cis and trans? Well, I think that in this case, if we look, we can draw this in a way that could look like it has cis and trans. But in this case, there's a whole different type of geometry here where where these things exist. So in this case, we're not going to talk about cis and trans here because there's not 4 things attached to it. Okay, and as we look around, you'll see that this has 6 things, this has 6 things, and this has 6 things. So none of these can be coordination compounds or coordination isomers. Okay, now geometric isomers. Let's look at question or problem number 2, or complex ion number 2. And so here, this appears to be the same sort of thing. And so geometric isomers, can these things switch back and forth? Well, there's no counter ion here. So because there's no counter ion, it can't switch with the ammonia or the chlorine. So that is not a geometric isomer. Is it a linkage isomer? Well, ammonia bonds to the cobalt only through the nitrogen. That's the only place that it has a lone pair. And chlorine isn't one of those chainy looking things. So there's no linkage isomers here. So complex 2 is nothing, is none of these. Okay? It could be a coordination isomer, but again, we're not really worried about that. About the overly difficult ones. Okay? Now complex number 3 here, again, cobalt in the middle. And now, look, we have Cl and Br, and then it has 5 ammonias, NH3. Ooh, you know what I would guess? I would hazard a guess that this looks like this with a Br out here. And that can now change the position with this, so that makes it a geometric isomer. So complex number 3 is a geometric isomer, but ammonia, again, is not something that can have linkage isomer. You can't change linkages, so it's not a linkage isomer. And then, again, we're only looking at things with 4 that could possibly be cis-trans isomers or coordination isomers. So that's the idea of isomerism, that different structures can exist for compounds that have the same exact formula. So, yeah, we'll practice this a little more next time we see each other.